In the last video, we saw how to solve puzzles with forces that point at oblique angles. In this video, we will apply this knowledge to an important application: ramps. A ramp is a surface that is inclined at an angle. Here we see a ramp with a 20-degree inclination. An object placed on a ramp will feel two forces at minimum. One is the familiar force of weight. The other is the normal force, but here there's a difference. The normal force is always pointed at 90 degrees perpendicular to the surface. Because the surface is tilted, that means the normal force must also be tilted. The normal force points off at an angle. It is no longer exactly opposite the weight. And that means the normal force can no longer perfectly cancel out the weight, and therefore this object will accelerate. But before we solve for acceleration, let's see how to analyze the free body diagram. For ramp puzzles, the y-axis is drawn in line with the normal force, that is, at 90 degrees to the surface of the ramp, and the x-axis is placed parallel to the ramp. It's perfectly legal to have tilted axes like this as long as they stay at 90 degrees to each other. Remember, axes simply represent your perspective on the motion, which direction you consider positive and which direction you consider negative. The motion of the object doesn't depend on your perspective, so we can pick our axes in whichever direction makes this puzzle easiest to solve. And as we'll see, perpendicular and parallel to the slope make this puzzle very easy to solve. Now, if the surface had been flat, the normal force would point vertically, straight up. But because we're on a 20-degree incline, the normal force must be 20 degrees away from the vertical. A little geometry, and we can figure out that the weight force must therefore be pointed 20 degrees away from the y-axis. We need to know this because the weight force is not aligned with either the x or y axes. That means we need to break it into components, and that's what we do. The x component is opposite the angle, so it is calculated as weight sine 20. The y component is adjacent the angle, so it is weight cos 20. Yes, you heard that right. For the first time, the sine component is in x and the cosine in y. That's because we found the angle of the weight with respect to the y-axis, not the x-axis. When you're doing ramp puzzles, you have to keep track of which components constitute the opposite side and which component constitutes the adjacent side. The cosine doesn't always get associated with x. A ramp offers something we haven't seen before. On a ramp, gravity is responsible for making things move, but for the first time, gravity is not causing free fall. The object isn't accelerating at 9.81 meters per second squared anymore. So we need to determine what the acceleration is. Consider this situation. A 5-kilogram block is placed on a frictionless ramp with an incline of 20 degrees. What is the acceleration of the block? We start by drawing a picture. When we draw the free body diagram, though, there's a wrinkle we have to account for. The weight force will point straight down as usual, and the only other force is the normal force. But by definition, the normal force always points at right angles to the surface the object is on. In this case, it will not point straight upwards as it did when the object was on a level surface, but at an angle. Now, let's draw the axes. In ramp puzzles, we have a convention that we always draw the y-axis in line with the normal force. As we've seen, the choice of how the axes point doesn't alter the motion of the object in the puzzle, it just establishes the perspective of the observer. It so happens that this way of setting up the axes makes the puzzle easiest to solve, and we'll see why later in this video. The way we've drawn it, the positive x-axis points down the ramp, and the positive y-axis points perpendicular to the ramp. In this way of drawing, the normal force is in line with the y-axis, but the weight force is pointed at an oblique angle with respect to the axis. As we saw in the last video, whenever a force points at an oblique angle, we have to break it into its components. The procedure is as follows. This is important and it's easy to make mistakes, so pay attention. Draw a vertical line upward from the spot on the free body diagram. If the object had been on a level surface, the normal force would have pointed along that vertical line. However, since the incline is 20 degrees, the normal force is tilted 20 degrees away from that vertical. Now, the y-axis is in line with the normal force, while the weight force is in line with the vertical. Using a bit of geometry, we realize that the angle between the weight force and the y-axis must be the same as the angle between the normal force and the vertical line, 20 degrees. We're now ready to break the weight force into its components. The component in y is adjacent to the angle, so its size is given by weight cos 20 degrees. The component in x is opposite the angle, so it is given by weight sine 20 degrees. No, that's not wrong. For the first time, we're seeing the cosine component in y and the sine component in x. That's because for the first time, the angle is being drawn with respect to the y-axis, not the x-axis like we usually do. We next find the forces in each direction. We set this equal to ma. The weight is unknown, but it's easily found, 49.05 newtons. Now, the block isn't moving in the y direction. It isn't collapsing into the ramp, nor is it levitating off the ramp. Therefore, its acceleration in y is 0. We can put all this information back into the force balance to find the unknown normal force, 46.09 j hat newtons. So much for the y direction. What about the x direction? There is only one force acting in the x direction. We set this equal to mass times acceleration. We now have enough information to calculate the acceleration, since we already calculated the weight. It's also important to note that the initial velocity of the block is not important in these questions. Whether the block is initially moving up or down the ramp, the same acceleration will result. So now we have solved for the acceleration of an object sliding down a ramp due to gravity. But in the real world, the sliding object would be experiencing friction as well. Suppose we rewrote the question like this. Everything remains the same, except that there's now a coefficient of kinetic friction between the two surfaces of 0.15. What is the acceleration now? We start similarly to before. However, the free body diagram is different. There is now an additional force of friction opposing the motion of the block. Now we see why it was so useful to have tilted axes. In ramp puzzles, all the forces ended up tilted, either to be perpendicular to the ramp, like normal force, or parallel to the ramp, like friction. Generally, the only force that is not aligned with the tilted axes is weight. Had the axes not been tilted, we would have had to split two forces into their components, the normal force and the friction force. But by tilting the axes, we only have to split one force, weight. The split into components occurs as before. Indeed, all the steps that lead to the setting up of the force balance in y and calculating the normal force and the weight force are exactly the same as before. The difference only comes in the x direction. The mass, weight, and angle are exactly the same as before. But unlike before, there is now a second force in the x direction, a kinetic friction that must be subtracted in the force balance. We need to calculate the kinetic friction. This is straightforward to do using the formula from the last video. the coefficient of kinetic friction times normal force. Plugging this in and solving, we find a new acceleration I hat meters per second squared. We can use other forces as well, like the applied force. Consider this puzzle. Someone pushes a 5 kilogram object up a 10-degree frictionless ramp. They apply a force of 25 newtons. What is the acceleration of the object? We'll start by drawing a picture. Here's a ramp. Here is a 5 kilogram object that is being pushed along it. There's our hero pushing it. The incline of this ramp is 10 degrees. And we want to find out what the acceleration of this object up the ramp is going to be. We were told that our hero is pushing it with 25 newtons of force, and we are ignoring kinetic friction. So, let us draw the free body diagram. As far as this 5 kilogram object goes, there are 3 forces acting on it. First, there is weight pointed downwards. There is normal force, which is always pointed at right angles to this surface. So if the surface looks like this, then the normal force has to look something like this. And finally, there is the push of our hero over here. And the push of our hero has a size of 25 newtons. This would be an applied force over in this direction. So that's the full force balance, or more correctly, the full free body diagram. Now, let us set our origin and axes. The y-axis in a ramp question is always set along the normal force. Now, over here, what we see is that our hero is pushing this object up the ramp in this direction. That means that the applied force must be along the ramp. So the applied force is going to be along the x-axis, which is obviously going to be at right angles to this perpendicular. I'm going to set positive x in this direction. So now we see the normal force is along y, and the applied force is along x. The only force that we need to break into its components is weight. So let's go ahead and do that. If we were to draw a vertical line over here, like this dashed line that I've drawn here, then the normal force would be 10 degrees away from this line. Because if this had been a flat surface, the normal force would point straight up, a bit like that. But since this ramp is tilted by 10 degrees, the normal force must also get tilted off axis, away from the vertical, by 10 degrees. With a little geometry, we can say that this weight force must also be 10 degrees away from the y-axis, which is aligned with the normal force. So if this angle over here is 10 degrees, that means that this angle over here must also be 10 degrees. We are now ready to break weight into its 2 components. One component which is in line with the y direction, like that, and one component which is parallel to the x direction, like that. And these 2 components obviously will be at right angles to one another. Now, this component over here, which is in the x direction, is opposite the 10-degree angle. Therefore, this is weight sine of 10 degrees. Again, you heard that correct. The sine component is in the x direction because it is the opposite side of this angle. Sine and cosine do not have to do with x and y. They have to do with opposite versus adjacent. So that is something which is very easy to mess up on in questions like this, so make sure that you're careful. Now, if this side, this component, is the opposite side, that means that this component must be the adjacent side, which means it's associated with the cosine of 10 degrees. And now we have broken the weight into its two components. Weight cos 10 degrees, which is pointing in the y direction, and weight sine 10 degrees, which is pointed in the x direction. We are now ready to calculate what is the overall force occurring in the x direction. In the interest of time, I'm not going to bother with the y direction. We're going to see that when we redo this question with friction. But in the x direction, we can say that the total force is given by the applied force, which is in the positive direction, plus the negative weight sine 10 degrees, which is going to tend to pull this downwards. But the total force is also equal to mass times acceleration. So that means that applied force plus the negative weight sine 10 degrees is equal to mass times acceleration. Now, let's figure out what the weight is. The weight is equal to mass times gravity, which is equal to 5 kilograms times 9.81, which is equal to 49.05. That's the size of the weight force, 49.05 newtons. So the applied force is 25 minus 49.05 times the sine of 10 degrees. So that's the size of this weight force, or at least the size of the x component of the weight force. All of that is equal to the mass, 5, times the acceleration, which is unknown. So now, let's go ahead and solve this out. 25 minus 49.05 times the sine of 10 degrees gives us 16.48. So 16.48 is equal to 5 times acceleration. Divide both sides by 5. You get acceleration is equal to 3.296. Let's call that 3.3. And this would be I hat meters per second squared. This is the acceleration of the box as our hero is pushing it up the ramp.
Now, let's add friction. Suppose someone pushes a 5 kilogram object up a 10-degree ramp, again applying a force of 25 newtons. But this time, the coefficient of kinetic friction is 0.1. What is the acceleration of the object?
In this question, we have a ramp very similar to the last question. The object is still 5 kilograms, still being pushed upwards by our hero with the same force of 25 newtons, and the ramp has the same inclination of 10 degrees. The only difference this time is that there is a coefficient of kinetic friction here. And we were told that the coefficient of kinetic friction was 0.1. Now, let us draw out what the free body diagram would look like in this situation. The weight force is, as usual, going to point down. The normal force is, as always, going to point at right angles to the surface, kind of like this. Our hero is pushing it up the ramp, so that would be along the ramp like this direction,
There's our applied force. And finally, friction is going to point opposite the direction of motion. So since the box is moving up the ramp, friction has to point down the ramp. And this would be kinetic friction, like so. Now we are ready to draw our axes. I'm going to set positive y to be along the normal force, as we usually do in ramp questions, and I'm going to set positive x to be up the ramp. So we'll notice that the setup of this question, outside of the fact that we have this kinetic friction, is almost identical to what we did last time. Again, the only difference is we have kinetic friction this time. Now, the only thing that is not pointing along one of these axes is this weight force. So we need to find out how we can break this weight force into its components. Here's how we do it. Remember that the normal force always points at right angles to the surface of the ramp. It always points at right angles to whatever surface is supporting the object. Now, had this been not a ramp but just a flat surface, the normal force would have pointed straight up, like that. But because the ramp is tilted by 10 degrees, that means that the normal force has gone 10 degrees away from the vertical. So if we were to draw a line like this, we could say that this angle is 10 degrees, and with a little bit of geometry, that means that this angle over here is also 10 degrees away from the y-axis. So the weight force is angled 10 degrees away from the y-axis. The next step is to break the weight force into its components. So one component is going to be along the y-axis, and another component will be parallel to the x-axis. The component that is parallel to the x-axis is opposite this 10-degree angle. So that means this is going to be weight sine of 10 degrees. Again, the sine component is this time pointing in x because the sine component corresponds to the opposite side of the angle. With the angle located here, the x component is the opposite side. So again, don't be under some illusion that what is pointing in the x direction is always cosine. A lot of the time it is, but the correct way to figure it out is by looking at where the side is with respect to a given angle. Now, if this is the sine side, then this means that this has got to be the cosine side. Now, because friction is involved over here, friction is going to depend on the normal force. And in this case, we're going to need to work out how big that normal force is. We didn't need to do it in the earlier example because the object is not moving in the y direction. It's not collapsing into the ramp, and it's not levitating off the ramp. Therefore, its motion and its acceleration in y must be 0, which means the total force in y must be 0. Now, that doesn't matter when you have no friction to worry about. But where you do have friction, you need to solve for the normal force, so we need to attend to the y direction first. So, in the y direction, the total force is given by the normal force pointed up, that is in the positive y direction, and weight cos 10 degrees pointed in the negative y direction, which we could write like this. But total force is also equal to mass times acceleration. So the normal force plus the negative weight times the cos of 10 degrees is equal to mass times acceleration. Now we need to solve for the weight. Weight is equal to mass times gravity, which is equal to 5 times 9.81, which is equal to 49.05 newtons. That's the weight of our 5 kilogram object. We will take this information and we will plug it into this equation. So that gives us the normal force plus, or we don't even need that, let's just say minus 49.05 cosine of 10 degrees is equal to mass 5 times acceleration. In the y direction, the acceleration is 0 because it's not moving in the y direction. So this entire right side becomes 0. If I were to move this by adding it to both sides, I would say normal force is equal to 49.05 times the cosine of 10 degrees. And that is going to work out to 48.3. So we could say that the normal force is 48.3 J hat newtons. Now we're ready to turn to the x direction. In the x direction, the total force is given by the applied force, which is pointed up the ramp in the positive direction, minus, there are two forces pointing in the negative direction. One is the kinetic friction. So I could write it like this. And the other is the sine component of the weight, which I could write like this. Again, total force is equal to mass times acceleration. So we now have the applied force plus the negative friction force plus the negative weight sine 10 degrees is equal to mass times acceleration. So, a fair bit to figure out over here. The weight we already know from the earlier part of this question where we solved for it. The force of kinetic friction is easy to find out because force of kinetic friction is equal to mu sub k, the coefficient of kinetic friction, multiplied by the size of the normal force. Now, mu sub k, we were told, is 0.1. And the normal force was 48.3. We solved that just a moment ago. So that's going to give us a friction force of 4.83 newtons. So let's plug everything that we know into this equation. The applied force, 25, minus friction force, 4.83, minus the weight force. We already worked out that the weight force was 49.05. This was in the y direction that we worked it out. And this time we're going to take the sine of 10 degrees, so we need to multiply it by the sine. All of that is equal to the mass, 5, times the acceleration. So, 25 minus 4.83 minus 49.05 times the sine of 10 degrees gives us 11.65. So 11.65 is equal to 5 times the acceleration. So the acceleration is 11.65 divided by 5 is 2.33. And this would be in the I hat direction, and this would be in meters per second squared. So this is the acceleration of the block up the ramp. Notice that this acceleration is quite a bit smaller than what it was when we didn't have friction. It was about 3.3 when we had no friction, but it's 2.3 when we do have friction. So this is how we solve a question, a ramp question, where someone is pushing up a ramp and there is no friction. Or sorry, where there is friction.
What if we get a spring force involved as well? A 4 kilogram object is at rest on a 30-degree ramp. It is supported by a spring that is aligned parallel to the surface of the ramp. The spring constant is 100 newtons per meter. What is the compression of the spring?
In this question, we have an object which is sitting on a ramp, and it is supported by a compressed spring. The object has a mass of 4 kilograms. The inclination of the ramp is 30 degrees. The spring constant, K, is 100 newtons per meter. That's not a very stiff spring. That's a pretty flimsy spring right there if the spring constant is only 100. So now, let us draw the free body diagram for this object. Interestingly enough, we were told it wasn't moving. So it's going to feel the familiar weight force down. The normal force always points at right angles to the surface that is supporting the object, so that means it's going to point off in this direction. And finally, this object is being supported by the spring. So since the spring is compressed in this configuration, the spring is going to push it up the ramp. So the spring force points like this. I'll call this FSPR so we don't confuse it with static friction. So this then is the free body diagram. The next step is to draw in the axes. In any ramp question, the y-axis is always put in line with the normal force. The x-axis is always along the ramp. So the y-axis is perpendicular to the ramp, like the normal force, and the x-axis is along the ramp. I'm going to set upwards as positive. Now, we have this normal force, which is at right angles to the surface. Had the surface been flat, then the normal force would have pointed straight upwards, like so. But because it's tilted by 30 degrees, the normal force has also moved 30 degrees away from the vertical. So the angle between this vertical dashed line that I've drawn and the normal force is 30 degrees. And that means that the angle between the y-axis and the weight force must also be 30 degrees. Now, let's take the weight force and let us break it down into its components. There is one component which is pointed along the y-axis, and there's a second component which is pointed in the negative x direction. The component which is in the negative x direction is opposite this 30-degree angle. So that means that it is described as weight sine of 30 degrees. Meanwhile, the component which is along the y direction is adjacent to this angle. That will be weight cosine of 30 degrees. So, now we have broken down the weight force into its two components. Let's take a look at what is happening along the x direction. Again, we can ignore the y direction in this puzzle because the y direction is really only necessary if you need to find the normal force, and that in turn is only necessary if you have a friction in this puzzle. In general, in a ramp puzzle, and in most sorts of puzzles, if you don't have a friction force and the object is not moving in the y direction, it's not collapsing into the ramp or levitating off the ramp, we don't need to bother with the y direction. So we shall focus just on the x direction. Again, y direction only if there is friction or the object is actually moving in that direction. In the x direction, the total force is given by the spring force pointed in the positive direction minus the component of weight which is in the negative x direction. That's weight sine of 30 degrees. But total force in the x direction is equal to mass times acceleration in the x direction. So we can combine these to say that the spring force plus the negative weight force sine 30 degrees is equal to mass times acceleration. Let's solve for the weight force. The weight force is equal to the mass times gravity. The mass, 4 kilograms, times the gravity of 9.81. That works out to 39.24 newtons. So now we have a spring force minus 39.24 times the sine of 30 is equal to mass of the object, 4, times an acceleration. Well, this object isn't moving, so the acceleration would be 0. Now, 39.24 times the sine of 30 degrees gives us 19.62. So if I were to simplify this, this right side becomes 0, and I can move this to the other side to say that the spring force is equal to 19.62 newtons. And this would be pointing, by the way, in the I hat direction. Now, what were we actually being asked for? We were being asked for the compression of this spring. If you think back to what the definition is of the spring force, the rule is that the size of the spring force is equal to negative K times the displacement of the spring, or the compression of the spring. So, since the spring force is 19.62 I hat, that must be equal to negative K, which was 100, times the displacement. Actually, I should not have these absolute value bars over here. These should be parentheses, not absolute value. 100 times delta x. So, divide both sides by negative 100, and you wind up with the displacement of the object, or equivalently the compression of the spring, is equal to negative 0.1962 meters in the I hat direction. So this object descended down the ramp and compressed the spring by 19.62 centimeters, or equivalently 0.1962 meters. That is the compression of the spring that is required so that the spring can push up in the opposite direction and prevent any motion.
My 101 students can stop here if they want. My 103 students should watch these last two examples, which integrate pulleys into ramps. A frictionless ramp has a light frictionless pulley wheel attached to the top. The ramp has an inclination of 15 degrees. A 3 kilogram object sits on the ramp, and it is tied to a light string. The string passes over the pulley wheel. At the other end of the string is a 2 kilogram object. What is the acceleration of the objects?
In this question, we have a ramp and a 3 kilogram object sitting on the ramp, but this time we have additionally a pulley. A 2 kilogram object is strung from the pulley, and the rope goes over and attaches to the 3 kilogram object. The inclination is 15 degrees, and we are told that there is no friction. In this situation, we want to find out what the acceleration of the 3 kilogram object will be. Now, we're going to have to tap into what we saw in the video about pulleys. We know that in a standard pulley, the wheel is very light, the tension is consistent throughout the rope, and the acceleration of the 3 kilogram object and the acceleration of the 2 kilogram object have to be the same thing. Why are they the same? Because if the accelerations were not the same, then either the rope will bunch up or the rope will snap. Let's start with the 2 kilogram object. Because we have two different objects over here, we need to draw two different free body diagrams. So for the 2 kilogram object, the free body diagram is going to consist of the weight pointed down. Let's call that weight sub 2, so we know we're talking about this 2 kilogram object. And the tension force, which is pointed up. For the 3 kilogram object, we're going to have its weight pointed down. Call that weight sub 3. The normal force always points at right angles to the surface, like that. So the normal force points off at an angle like so. And the tension force is going to point up the ramp. So we now have the free body diagrams for the 3 kilogram object and for the 2 kilogram object. Now we are going to solve this using the same sorts of techniques that we have seen both in the ramp puzzles and in the pulley questions that we've seen so far. This will apply in terms of how we set our axes. So because I know this 2 kilogram object is going to descend over here, I'm going to set downwards as being the positive y direction for it. So the origin obviously always goes on the object, and downwards will be the positive direction. For the 3 kilogram object, I'm going to set upwards, up the ramp, as being the positive direction. And of course, we always set the y-axis to lie along the normal force. Now, this way that we have drawn our axes for the 3 kilogram object, we need to break the weight down into its components. If the normal force had been on a flat surface, it would have pointed straight up, like that. But because it's on a tilted surface, it gets pulled away from the vertical by 15 degrees, the same as the angle of inclination. So that means that the angle between the vertical and the normal force is 15 degrees, and therefore the angle between this weight and the normal is also 15 degrees. Now, let us break this weight into its components. There is one component which is going to point in the y direction, and there's one component which points in the x direction. In the x direction, the component is opposite this 15 degree angle. The opposite side is always associated with the sine. So the size of this x component is weight sine 15 degrees. The component which is in line with the y direction is going to be adjacent to this angle. That would be weight cos 15 degrees. Weight of the 3 kilogram object cos 15 degrees. So now we have broken this 3 kilogram object, its free body diagram, into its components, and we are ready to analyze the motion of these two objects. Now we're going to run into a conundrum over here because the tension is unknown, and we now have two objects which are moving. The tension is unknown and the acceleration is unknown. We're trying to solve for the acceleration, of course. So we are going to need two different equations in order to solve for the two unknowns, tension and acceleration. Let's start by setting up the force balance for the 2 kilogram object in the y direction. So for the 2 kilogram object in the y direction, we have the weight pointed in the positive direction. So total force is equal to weight pointed in the positive direction plus the negative tension pointed in the negative direction. So this is how we would symbolize the fact that it's pointed in the negative direction. The total force is equal to mass times acceleration. So that means that the weight of this 2 kilogram object plus the negative tension is equal to mass times acceleration. So how big is the weight? This is the weight of the 2 kilogram object. The weight of the 2 kilogram object is given by mg, which is equal to mass 2 times gravity, 9.81, which is equal to 19.62 newtons. So plugging in everything we know, we get 19.62 newtons minus however big the tension is equal to the mass of this object, 2, times the acceleration, which is unknown. So this is the first relationship that we have between the tension and the acceleration. I'm actually going to write this just a little bit differently. I'm going to move the tension over to one side and the acceleration over to the other. So that'll give us 19.62 minus 2 times the acceleration is equal to the tension. We will use this in our further calculations. Now, let's take a look at the motion of the 3 kilogram object. Because this object is not collapsing into the ramp, nor is it levitating off the ramp, there's no overall force occurring in the y direction. And since we are ignoring kinetic friction, or we're saying that there is no kinetic friction in this question, there's nothing else that depends on the y direction. So we can get away with not solving for what's happening in the y direction in this question. The interesting stuff is happening in the x direction, where we have the total force being given by the tension, which is pointed up the ramp, plus negative weight 3 times the sine of 15 degrees pointed down the ramp. The total force is equal to mass times acceleration. So the tension plus negative weight sine 15 degrees is equal to mass times acceleration. The weight of the 3 kilogram object is given as mg, which is equal to mass 3 times gravity, 9.81, which works out to 29.43 newtons. So that's the size of the weight force that's acting on this object. Tension minus 29.43 times the sine of 15 degrees is equal to the mass of this object, which is 3, times the acceleration, which is unknown. So, simplifying this, we get 29.43 times the sine of 15 degrees is 7.62, let's say. Which is equal to 3 times the acceleration. Now, if you'll remember from when we solved the y direction, we said that 19.62 minus 2 times the acceleration was equal to the tension force. We solved that out using the 2 kilogram object. So now we can take this expression and plug it in for the tension. 19.62 minus 2 times the acceleration gives you minus in turn the 7.62 gives you 3 times the acceleration. Simplifying all of this, 19.62 minus 7.62, that will give us 19 minus 7, that is 12. And the 2a we can move to the other side, so we get 12 is equal to 5a. So we conclude that the acceleration is equal to 12 divided by 5, which is equal to 2.4 I hat meters per second squared. So that is the acceleration of the 3 kilogram object up the ramp, and 2.4 j hat meters per second squared would be the acceleration of the 2 kilogram object down the side.
And now let us apply friction here as well. A ramp has a light frictionless pulley wheel attached to the top. It has an inclination of 15 degrees as before. A 3 kilogram object sits on it as before, again tied to a light string passing over the pulley wheel attached to a 2 kilogram object. But this time, the coefficient of kinetic friction between the block and the ramp is 0.2. What is the acceleration of these objects?
Now let's consider this question. So we have our object, which is sitting on the ramp. We still have a pulley wheel, and we still have a second object, which is dangling over the side, and the two are roped together like that. The mass of the first object, the one on the ramp, is 3 kilograms. The hanging object, 2 kilograms. The angle is 15 degrees. And this time, it's a little bit different because mu for kinematic, the kinetic coefficient of kinetic friction is 0.2. So, this is our full picture. Let us draw the free body diagram for the 2 kilogram object. It feels weight down, and it feels tension up. And those are the only two forces that it is feeling. What about the 3 kilogram object? Well, it would feel weight down, much the same as before, but it would also feel a tension pointed up the ramp, there's also a force of friction which is going to oppose the motion, that's going to point down the ramp. And we're going to assume that this is already moving, so this is a kinetic friction. And the last thing that we need is the normal force. Remember that the normal force always points at 90 degrees to the surface that you're on. So that means the normal force will point something like that. So this is the free body diagram for the 2 kilogram object, and this is the free body diagram for the 3 kilogram object. Now, let us set origin and axes. For the 2 kilogram object, I'm going to put my origin at the spot, as you must do in any force question, and I'm going to set downwards as my positive direction. Here is the origin for the 3 kilogram object. I'm going to set upwards as being the positive x direction, up the ramp that is, and this direction as being positive y. Now, what we see in the y direction, or what we see for the 3 kilogram object rather, is that there is now a single force, the weight, which does not point in either x or in y. So we need to break the weight into its components, and that's precisely what we do. Now, let's think back to what our process is. We know that for a ramp, the normal force always points at right angles, perpendicularly, 90 degrees, to the surface of the ramp. Here is a vertical line. Now, if the ramp if this had been a flat surface, not a ramp, then the normal force would point straight up. But because this is tilted by 15 degrees, that means that the normal force is now 15 degrees away from the horizontal, from the vertical. Which means that this angle is 15 degrees, which means that this angle is also 15 degrees. So we can break our vector over here like this. And we now just need to figure out which side is which. This side, which is pointed in the x direction parallel to the x-axis, is opposite this angle. So that means that this side has got to be W3 sine 15 degrees. Again, in this case, the sine component is on the x-axis, as it has been a couple of times in this video. So you don't blindly assume that sine is associated with x and cosine with y. You have to consider sine as being the opposite of whatever your angle is, wherever it is. And of course that means that this side is W3 cos 15 degrees. So far so good. We now have the complete breakdown of the forces over here. So let's go forward and let us solve for what is happening in the y direction for the 2 kilogram object. So for the 2 kilogram object, the total force in the y direction is going to be the weight 2, which is in the positive direction, plus the negative of the tension, which is pointed in the positive direction. I don't really need to write total force in y. I'll just say that for 2 we're interested in the y direction. So the total force is equal to mass times acceleration, and so we now have the weight of the 2 kilogram object plus negative tension is equal to mass times acceleration. Now, how big is the weight? Weight is given by mg, which is in this case equal to 2 times 9.81, which is equal to 19.62 newtons. So, plugging in everything we know, we get 19.62 minus tension is equal to mass 2 times the acceleration, which is unknown. I'm going to rewrite this slightly into 19.62 minus 2 times the acceleration is equal to the tension. So I just added tension to both sides and subtracted 2a from both sides. So we're going to use this expression over here to find out what the acceleration of this object is. Now we can turn to what's happening to the 3 kilogram object. For the 3 kilogram object, we have forces acting in both x and y, but one of those in x is the kinetic friction. The kinetic friction depends on the normal force. So let's solve for the y direction first. Even though this object is not moving in the y direction, it's not collapsing into the ramp and it's not levitating off the ramp, that means that even so, there's no acceleration here, but we will need that normal force to solve for the friction force. So here we have to solve y first. So for the 3 kilogram object in the y direction, we have total force is equal to, we have the normal force plus negative weight times the cos of 15 degrees. But total force is equal to mass times acceleration. So combining these two, we get normal force plus negative weight cos 15 degrees is equal to mass times acceleration. Now, this is the weight of the 3 kilogram object specifically. So let's work out what that is. The weight of the 3 kilogram object is given by mass times gravity. So the mass, 3, gravity, 9.81. And that works out to 29.43 newtons. So let's take this information and let's put it into this equation over here. The normal force minus 29.43 times the cosine of 15 degrees is equal to the mass, 3, times the acceleration. But the acceleration in the y direction is 0. So this entire right side is 0. So we now just need the value of 29.43 times the cosine of 15 degrees. So n is equal to 29.43 cos 15 degrees, which is 28.43. And this would be in the j-hat direction if we want to be absolutely rigorous about it. Now, let's take a look at the 3 kilogram object and its motion in the x direction. There is one force pointed in positive x. That is the tension force. There are 2 forces, however, pointed in the negative direction. One is the friction, and the other is the sine component of weight. So that would be T plus negative force of friction plus negative W3 sine 15 degrees. Now the total force is equal to mass times acceleration. So let's plug these two equations together. Tension plus negative force of friction plus negative weight of 3 sine 15 degrees is all equal to mass times acceleration. The tension is unknown, but the weight is known, the mass is known, and we can solve for the value of the friction, rather. So the value of friction is equal to mu sub k multiplied by the normal force. Mu sub k, we were told, was 0.2, and earlier we solved for the normal force, 28.43. So the force of friction is going to be 0.2 times 28.43 is 5.686 newtons. Okay, so we now have tension minus 5.686 minus the weight of this 3 kilogram object we already calculated was 29.43, and the sine of 15 degrees is equal to mass 3 times the acceleration, which is as yet unknown. So 5.686 plus 29.43 times the sine of 15 degrees gives us 13.3. So simplifying all of this, we get the tension minus 13.3 is equal to 3 times the acceleration. Tension minus 13.3 is equal to 3 times the acceleration. But we saw earlier that there was another relationship between the tension and the acceleration that we had worked out. And that was that 19.62 minus 2 times a gives you the tension. So let's plug that in for the tension. So we have this equation, T equals 19.62 minus 2a, which we got from solving out the motion of the 2 kilogram object. And the second equation, T minus 13.3 equals 3a, which we got from analyzing the motion of the 3 kilogram object. Now we just need to combine these two together. I can plug in 19.62 minus 2a for t over here. So that gives us 19.62 minus 2a minus 13.3 is equal to 3a. So simplifying all of this, I can move the 2a to the other side by adding it on both sides. 19.62 minus 13.3 is going to give us 6.32 is equal to 5a. And so we get an acceleration of 1.26 meters per second squared. So this would be in the positive x direction if you're talking about this object here, the 3 kilogram object, and it would be in the positive y direction for the falling 2 kilogram object. This is quite a bit smaller than what happened when we had only the tension and the weight acting on the 3 kilogram object without the friction. It was about 2.4 in that case.
It's possible to create increasingly complicated ramp puzzles, but they would still all be solved by the techniques we have already seen in this video and the past several videos. The most valuable lesson of this topic might be the reinforcement of the fact that we can always set the axes how we wish to make the puzzle easy to solve.